Can we sort in linear time? Welcome to another video on the sorting problem. So in the sorting problem, we have given a sequence of numbers and we want to find a permutation, so a reordering of those numbers such that the numbers are then in increasing order. And sorting is a fundamental problem in algorithms. It has lots of applications. I in particular like it because I can use it to explain various algorithmic techniques. So what is a specific question for today? The question is, how fast can we actually sort? So at this point, I assume you know insertion sort and you know merge sort. So insertion sort runs in quadratic time. And there we can ask, can we do faster? And the answer is yes, we can do faster. And we know that we can do faster because merge sort is faster. It's much faster. It runs in order n log n time. But then when we design algorithms, the natural next question is, can we do even faster? So can we, for instance, solve the sorting problem in order n log n time or even linear time? So that's what we're going to look at today. If we want to argue about how fast we can solve a computational problem, we need to think about how can we actually prove upper and lower bounds on how fast a problem can be solved. So the easy part here are the upper bounds, because that's what we have already been doing, implicitly at least. So if I want to show that I can solve a problem in order f of n time, how do I do that? I can simply do so by giving an algorithm. So if I want to show the sorting problem can be solved in order n log n time, then I can show that by giving merge sort, showing that merge sort indeed runs in that time, and I'm done. So the lower bounds, those are actually much trickier, and it's actually quite difficult to show lower bounds on computational problems. For sorting, luckily that will, to some extent at least, be possible. So how do we show that a problem, a computational problem, cannot be solved faster than in order f of n time? So for that, we have to prove for every algorithm that solves a problem that it runs in at least order f of n time. So for that, we have to argue about the set of all algorithms, and that there we have to be careful. Because what is an algorithm? That's a question that we essentially also need to answer when we want to prove something about every algorithm. And that brings us to computational models. So very often we don't explicitly talk about computational models, but if we want to show lower bounds, we have to state something about the model that we are using. So in computational models, typical questions are, do we allow bit manipulation? So how many bits can I change at the same time? Or do I allow random access? So when we work with arrays, we take random access for granted, but there are also models like pointer machines where that is not given. For sorting, we can actually work with a very simple model, and I explain that by the example of insertion sort. So here you see insertion sort, and what we can observe here is that all of the decisions that the algorithm takes are based on comparisons between input elements. So instead of counting all the precise steps that the algorithm does, what we will count is the number of decisions that the algorithm is taking. So let me illustrate that by an example. So let's assume our input are three numbers, A0, A1, A2. Now the first thing that the algorithm does, okay, it sorts A0, it doesn't do anything. What it then does, it compares A1 and A0. Depending on which one is smaller or larger, it will swap A0 and A1. So if A0 is smaller equal A1, then it will not swap. If it's larger, it will swap A0 and A1. Now, next, what insertion sort does, so now we've done with A0 and A1, we can assume that they are sorted. Now we take A2 and want to add it to this. So if A0 was smaller equal A1, then currently here at this point, so here we still have them in order A0, A1, A2. Now I will compare A2 with A1. Now, if A2 or if A1 is smaller or equal than A2, that means there's no swap, then we're actually done. So what we then have is that the sequence actually still is A0, A1, A2, so we didn't have to sort at all. If A2 is smaller or equal to A1 at this point, then we will swap A2 and A1. So that's here. So at this point we have A0, A2, A1. Now, in this case, we still have to compare A2 and A0. 0 and 2. If A0 is smaller, we're done. So then we have here A0, A2, A1. If A2 is smaller, then we need to swap. So then we will get A2, A1, A0. And we can do the same thought experiment when we had to swap A0 and A1. So in this case here, so at this point we have A1, A0, A2. Now the first thing that we will do is we compare A0 with A2. If A0 is smaller, we're done again, and we have here A1, A0, A2. Otherwise, we then have to compare A2 and A1. 1 and 2. And based on that comparison, so if 1 is smaller, we are done. So then we keep A1, A2, A0. And otherwise, we need to swap A2 and A1. So then we would get A2, A2, A1, A0. So what we have here is we have compressed the algorithm to the decision that it is making. So, and instead of counting the operations, all the operations, we simply count now the number of comparisons that it did. So what we see is to sort 3 numbers, insertion sort in the worst case uses 3 comparisons, namely in this path here. And that will be our approach to proving lower bounds. Namely, we will prove that any sorting algorithm in such a tree, which we call the decision tree, needs at least a certain number of comparisons. That is any comparison-based sorting algorithm. Let's have a quick quiz. Which of the following sequences of comparisons does not result in a longest path from root to leaf? So is it smaller equal and then lots of larger? So the question is which of these paths is not the longest? This one, or this one, or this one? The correct answer is B. So this path here. So why is that not a longest path, and why are the other 2 longest? So in this rightmost path, what happens? So that is kind of corresponds to a worst case input where the numbers are in decreasing order and where I essentially have to do all the swaps. And with each comparison, we're actually doing a swap. This sequence here is actually also a kind of worst case input. There, what happens is we're not swapping A0 and A1, but it doesn't save us anything because the comparison between A0 and A1 happens anyway. So we're saving a swap, but we're not saving a comparison. And after that, it's worst case as the rightmost path, because we're doing all the swaps, and with every swap, we're actually also doing a comparison. In contrast, B, okay, so we have the first comparison. After that, we always have a smaller equal. And what does that mean at that point? It means as soon as we have a smaller equal, we equal, we stop looking further to the front. So in that way, this actually corresponds to an execution of the algorithm where we only have a linear number of steps and a linear number, therefore a linear number of comparisons. Yeah, so in B, actually the number of comparisons is linear. In A and C, the number of comparisons that we do is quadratic. Let's take a closer look at decision trees and how we use them to prove a lower bound for sorting. So here's a decision tree. We've seen decision trees for insertion sort. So this is just a general decision tree where the internal node corresponds to a comparison. And that could be smaller versus larger equal. What we saw for insertion sort was smaller equal versus larger. It could also be equal versus not equal. It's a decision where we're comparing two input elements. And we assume that all the decisions that our algorithm takes are decisions of this type where I compare two input elements. So between two decisions, the algorithm can perform other operations as long as it doesn't take any decisions. So it can swap as much as it wants to. We don't care. We only count the number of comparisons. So you can imagine you get an input, then the execution of the algorithm will correspond to a path in this tree. When we reach a leaf, then the algorithm is done. And with a different input, we may follow a different path, and when we reach a leaf, we're done. And the number of comparisons, so given an input, the number of comparisons that we do corresponds to the length of this path. So if I want to say something about the worst case running time of an algorithm or worst case number of comparisons, I need to look at what is the longest path from the root to any of the leaves. And what we now want to show is a lower bound for sorting. We want to show that the longest path here to a leaf will have at least a certain length. So we want to prove a lower bound of f of n comparisons. And we'll do so by using a proof by contradiction. Meaning, we're going to assume that the worst case number of comparisons is actually less. So we assume there's an algorithm that never needs more than f of n minus 1 comparisons. So what does that mean in terms of the tree once more? It means that for this algorithm, any path from the root to a leaf cannot be longer, will not have more comparisons than f of n minus 1. So here we have our tree. It might have shorter path, but it will not have any longer path than f of n minus 1. So that gives us a bound on the height of the decision tree. And we're going to use this now to prove that if the height of this decision tree is too much bounded, so too small, then there will be two different inputs that reside in the same comparisons. So that means they're going to follow the same path in this decision tree. But if I have two different inputs, and so in particular what I'm going to look at is two different permutations of the same numbers, if they both follow the same sequence of comparison, therefore following exactly the same execution sequence, it means the algorithm does the same for the two different permutations. So it cannot permute them in the same way. So imagine, for instance, you had A0, A2, A1, and A2, A0, A1. And I know that both of these follow exactly this path. It means that the algorithm does exactly the same thing on these two inputs. But that means that if this one afterwards would be sorted, A0, A1, A2, if the algorithm does exactly the same on this sequence, then A2, which was initially here, will still sit here. A1 that was here and here, A1 will be here, A0 will be like this. So if they have the same sequence, it cannot be that both of them are afterwards sorted. And that will be our contradiction. And that means the algorithm cannot be correct. That means that if this happens, we will need more comparisons. So once more, the approach is we count the number of different inputs, so this will be the different permutations of A0 to an minus 1. They all will need different outputs, or different path in the tree, meaning they all have to correspond to different leaves. So if I can bound the number of leaves depending on the height, I am done. Let's do one more example to see this, and that is merge sort. So let's say I have merge sort now on 4 numbers. So now I have A0, A1, A2, A3. Let's draw the decision tree for merge sort, or at least partially. So what happens first is, okay, I recurse. So then I have A0 and A1 on one side, A2 and A3 on the other side, and then I will compare A0 and A1. That will be my first comparison. And actually, independent of what happens in that comparison, what I will do next, so I mean, I might swap A0, A1 or not, but the next step will be that I will sort A2 and A3. So here I have 2 and 3. Here I have 2 and 3. And again, let me do a smaller equal, larger. So let's look at this leftmost path. 0 was smaller, it's still at the front. Then we have 1, 2 and 3. 2 was smaller. So right now we have 0, 1, 2, 3, still in that order. Next we would be comparing 0 and 2, because we're merging the two sequences. We're merging the sequence A0, A1 and A2, A3. So we're comparing 0 and 2. And then if 0 was smaller, we're then comparing 1 and 2. Then if 1 was smaller, we're done. So then we still have A0, A1, A2, A3. If 1 is larger than 2, then we still need to compare 1 and 3. 1 and 3. And depending on that comparison, if 1 is smaller, we will get A0, A2, A1, A3. And here we will get A0, A2, if 3 is smaller, A3, A1, and so on. So let me not draw this part of the tree, but this is part of the decision tree for merge sort. So what you see here now is that we have a path with, so this path, it uses 1, 2, 3, 4, 5 comparisons. The question is, can we do better? So can we sort 4 numbers such that we only at most need 4 comparisons? So it says something that on these 4 numbers is better than merge sort. So now let's think about what that would mean. It would mean we have a comparison at the top. Okay, we branch 1, 2, 3. Now we do our 4th comparison. And then the algorithm should terminate. And maybe the tree is even smaller, but this is kind of the largest tree that we could allow with at most 4 comparisons. And here we have the leaves, and so on. Yeah, what does and so on here mean? So how many leaves do I have? So here I have on the next to last level, I have 1, 2, 3, 4, 5, 6, 7, 8 nodes. So the number of leaves is 16 leaves. So that's the utmost that I can get if I allow, in the worst case, 4 comparisons. 16 leaves. Now if I look at the permutations of A0 to A3, then okay, I can have A0 first, A1, A2, A3, I have, so let me just do 0, just write the indices, 0, 1, 2, 3. I can have 0, 1, 3, 2. I can have 0, 2, 1, 3, and so on. So how many different ways do I have? That is the number of permutations. So the number of permutations of A0 to A3 is 4 factorial, so that is 4. So I have 4 options for what's at the beginning, 0, 1, or 2, or 3, times 3 for the next one, times 2. So 24 permutations, meaning that if each of these ends up in a different leaf, and each of these has to end up in a different leaf for the algorithm to be correct, otherwise there are 2 different permutations that do get exactly the same sequence, it means I need 24 leaves. That means that if I only allow 4 comparisons, I have too few leaves. If I have fewer leaves, then number of input element, number of possible inputs, it means that at least 2 inputs will end up in the same leaf, and that will give us our contradiction. So 4 comparisons are not enough because we only get 16 leaves. And with 5 comparisons, an optimal algorithm can do, because with 5 comparisons I can get 32 leaves. So in terms of the proof technique or idea that is used here, let me just briefly say that is called the pigeonhole principle. So the pigeonhole principle just says if I have, in this case, 24 possible inputs and only 16 places, then there are at least 2 of those that are at the same place. So in this setting here, I have n pigeonholes, m larger n pigeons, then at least 2 of the pigeons have to be in the same pigeonhole. That's the pigeonhole principle. So what I just showed by the example of merge sort and with 4 elements also works in general with n elements and general sorting. So if I have n elements, so A0 to n minus 1, I look at all different permutations. All different permutations of these elements will have to have different paths in the decision tree. What that means is that the decision tree needs to have at least n factorial leaves. So n factorial, that's n times n minus 1 and so on, and that's the number of different permutations that I have as inputs. Now, if I have n factorial leaves, what is the height of the tree at least? So for this, let's have a look at this tree here. So height 0 corresponds to only having 1 node. Height 1 corresponds to having these nodes here. This would be height 2. So let's say we have height 3. So first observe that if we want to maximize the number of leaves for a given height, the best is to have all of the leaves at the lowest level. So how many nodes do I have at the third level here? That is actually 2 to the 3, so 8 nodes. Or more general, if I know the height of the tree, the number of leaves is bounded by 2 to the height. What does that mean? It means that the height, so the logarithm of the number of leaves, is a lower bound on the height. Now, if I know that I have at least n factorial leaves, that means I know that I have at least log n factorial height. So the height of my tree is at least log n factorial. That means that the worst case running time, or the worst case number of comparisons, that is at least as long as the longest path from root to leaf, which corresponds to the height of the tree, of which we know that it is at least log of n factorial. So now we just need to know how much is log of n factorial. So log of n factorial is of order n log n. Why is that the case? So if we look at n factorial, which is 1 times 2 times 3 times, let's be somewhere n at n half, and now we have n half plus 1, n half plus 2, and so on. Eventually we end up with n. If you look at these terms here, those are n half many terms, each of size at least n half. So as a lower bound, I have n half times n half times n half, n half times. So I have a lower bound on n factorial of n half to the n half. But now if I take the logarithm, so if I take the logarithm here, let's take the logarithm here. So the logarithm of n factorial to the n factorial, the logarithm of a to the b is b times log of a. So this is n half times log n half, and that is of order n log n. N log n is also an upper bound because there's an upper bound here for n factorial. So n factorial is smaller than n to the n. And if I take logarithm of that, I get n times log n. So log n factorial is of order n log n. What do we see here? We see that the worst case running time is at least order n log n. This is exactly what we wanted to show. What this tells us is that any comparison-based sorting algorithm requires at least n log n, order n log n comparisons in the worst case. That in particular means we cannot do better than merge sort. So merge sort is optimal as far as comparison-based sorting algorithms go. Let's relax with a small quiz. What is the lower bound on the shortest path from the root to a leaf? So this is now any sorting algorithm, and I'm asking you, how short could a path be? Could a path from root to leaf be as short as 1? Could it be constant, order 1, n minus 1, or order n log n? The correct answer is n minus 1. So there cannot be a path that is shorter than n minus 1. What does that mean? It means that no matter what the input is, you at least need to do n minus 1 comparisons to check that input. So you can imagine, to verify that a sequence of numbers comes in sorted order, you'll need n minus 1 comparisons. Intuitively, that's clear. It's actually a bit trickier to argue than I just did. But that is the right answer here. So constant and 1 and constant is too little, and n log n is too much, because of course you can do with n minus 1 comparison. For the sequence of numbers that is already sorted, you just check whether it is sorted and then finish. So that would be n minus 1. This is about the shortest path, not about the longest path. So for instance, insertion sort, you can have very short path. You just also have very long path. Okay, that wraps up the part about lower bounds. Now here comes a bit of a surprise, possibly. Namely, after telling you that we need at least order n log n time for sorting, I'm now going to show you linear time sorting algorithm.